Hi guys, my name is Avishek Dusoye. I'm a PhD student at the University of Cape Town. My supervisors are Dr. Dumbriz and Peter Dansby. I will be talking about disformal coupling in a lambda CDM background cosmology. So this piece of work is available on arXiv. It was done in collaboration with Professor Nunes at University of Lisbon. So a quick motivation for this work is that so much evidence, including the recent Planck data, is pointing the presence of a dark energy and is proving how the lambda CDM is a successful model. So we moved toward theories that could mimic lambda CDM. That's the main concept. So let's dive in. So this is a summary of what I will be talking today. There are 6 main points. Um, so the first assumption that we are going to look at is this formal transformation. So just before I get into that, I want to say that um, in extending general relativity, some gravity theories might require two geometries. The metric so the physical geometry and the gravitational geometry. And the conformal transformation is a much simple relation connecting those two geometries. In GR, we have the conformal coefficient to be 1. And a lot of work has been done in this arena, but we move forward to the disformal transformation. So the conformal transformation basically only rescale the original length of the metric, whereas in the disformal transformation, we also consider the distortion of angle and length of the original metric, which arises due to compression and which occurs in the direction of the gradient of the field. So here we're considering an extra scaled kinetic term of the scalar field. Note that now we have a disformal coefficient to deal with. So, so this was one of the first assumption, but the main assumption, as I said, is our model, our gravitational model mimics lambda CDM. A quick overview of what I mean is we are working on a couple quintessence model. So basically, in this model, I have a scalar field, which is coupled to a fluid, and it is interacting, both of them. And this model is mimicking the cosmological background. So by that, the cosmological background has a cosmological constant and a fluid. Mostly, I refer it as an uncoupled fluid to cater for different scenarios. Now let's have a look at the model that we're working with. So constructing the model, here we go. This is the action. The Lagrangian of the scalar field has a kinetic term and a potential. So assuming the FLRW metric, one can obtain the Friedmann and Ricciardi equation. And but the variation of the action with respect to the scalar field gives us the modified Klein-Gordon equation, where Q is the coupling or the interaction term I was referring. So in the disformal framework, so when we consider the disformal transformation, this coupling takes this form. And you can see this in the reference to, I can show you the citation later. In our model, the conservation equation for the scalar field and the coupled fluids are given as below here. So we can see that there is a flux of energy from one fluid to another. And one can say that they are not conserved individually, but they are conserved altogether. And projecting this conservation equation alongside a co-moving observer, we obtain those continuity equation. Those are the equations that we will evolve and see how the system behaves. So briefly, in the cosmological background that the model is mimicking, so the lambda CDM background is very well known, and here we only considering two fluid, the lambda, a cosmological constant, and a uncoupled fluid. And as I said, the rho u is to cater for different scenarios. For instance, at early time, rho u could be radiation, and at late time, rho u could be dark matter. Equating those to cosmological background, one can express the scalar field in terms of the cosmological constant, and we can further obtain those Friedman and Ricciardo equations. Now, moving forward, um, we're going to apply the dynamical system approach to our model, our coupled quintessence model. So what I mean is, firstly, we define the dynamical variable as such. So the kinetic x square is the kinetic energy of the scalar field. Um, y square is the energy density parameter of the cosmological constant. Z square is the energy density parameter of the coupled fluid, and sigma, which measures the strength of the disformal coupling. Also, because we are dealing with the disformal transformation, I mentioned the first point, we have to specify the conformal coefficient and the disformal coefficient. But essentially, we will be dealing with alpha and beta, which are two constant parameters used in our analysis. When we set beta to 0, we have a purely conformal framework. And the last thing I would say here is note the m, mass, which influences the disformal coefficient. Now, we're going to plug in the dynamical variables into the continuity equation, the one that I'm showing now. And also note that the couplings are here. And what we obtain is a system of first order differential equation with respect to the E-fold. So this system is firstly dependent on the two equation of state for the two generic fluid that we have been dealing with and the couplings. So basically I have so much generality to work with in terms of the model mimicking lambda, a cosmological constant, and Q, I can both have a conformal framework and a disformal framework. Now, because I have the two generic fluid, I can specify the three study scenarios that we are dealing with. The first scenario is one which implies that, for instance, dark matter is coupled to the quintessence, and it's mimicking an exact lambda CDM as from the matter-dark energy equality. In the second scenario, we have a relativistic fluid, which is coupled to the quintessence, and both are mimicking an exact lambda CDM background again. And in the third scenario, what we have is a relativistic fluid coupled to the quintessence, and these fluids are mimicking an early universe of lambda CDM. Or another example of this could be how neutrinos were coupled in early universe and decoupled later on. So in our dynamical system analysis, we solve our system of first order differential equation. And what we get are two solutions, the fixed points, which are static solutions, which happens at x prime, y prime, and z prime, sigma prime is equal to 0. And our trajectories, which are non-static solution of the dynamical variable. These basically correspond to the evolution of the dynamical system from one cosmological state to another on a compactified phase space. Um, so, just give me a sec. So, um, we're going to dive into when our coupling are purely conformal. That is when D is equal to 0, sigma is equal to 0, and beta is equal to 0. So this is the solution that we have. And for the three scenarios, this is what we obtain. So the blue dots represent the fixed points that I was talking about, and A naught is a scalar field dominated attractor. The C plus and C minus are two kinetic dominated saddle points, and the yellow regions correspond to a region of accelerated expansion. In scenario 2, there's a red line. This is an equilibrium point consisting of a repeller fixed points. It separates x is equal to less than 0 and x greater than 0. Particularly when we simplify our dynamical system, the first order differential equation, they actually simplify into much simple system. Although I'm not showing it here, but in scenario 2 and scenario 3, those equations do not depend on the parameter alpha. And moving on to the disformal framework. So basically, now we have sigma makes a difference and D is not necessarily equal to 0. Let's dive into one of the scenarios. What we find is, firstly, so this is the disformal solution where we have fixed the parameters alpha and beta, but we are starting the evolution of the system from various initial conditions. So what we see here is a 3D phase portrait of X, Z, and capital sigma. Capital sigma is arctan of sigma. We do this so that we can compactify from minus infinity to infinity into a compact phase space. And what we see here is that, what we see here is that sigma, or capital sigma, gives an extra degree of freedom for the dynamical system to evolve. Where on the x, z plane is a purely conformal framework, because this is where sigma is equal to 0. The orange region correspond to where the disformal transformation is not real. So basically it goes down to a complex number. And in scenario 1 in particular, what we find is we have three disformal fixed points. We have a line of equilibrium points, and we have a plane of fixed points as well. So what one can see that the dynamical system flows from one fixed point to another within this compactified space, and the point S plus and T plus are asymptotes. We can also see that the dynamical system is sensitive to chosen initial condition. What I mean is, if the initial condition is chosen near C plus, the dynamical system ends up either near A naught, which is the attractor, or the equilibrium line S plus, or the equilibrium yeah, exactly. Now, dealing with the trajectories, what we find that we can also fix the initial condition and try to investigate the different effect of alpha and beta. And basically what we see is obviously the fixed points are the same, everything is the same. It's the trajectories which will be different. For alpha is equal to 0, the trajectories flows in the region bounded by x greater than 0, and for alpha less than 0, the trajectories flow in the region bounded by x greater than 0. So basically, a larger value of alpha causes the trajectory to pass nearer to the conformal point C plus minus before ending at the attractor or on the equilibrium line. I won't get into much detail, but what I would say is the parameter alpha and beta determine how much the dynamical system gets influenced by either the conformal fixed point C plus, C minus, or the disformal fixed point S plus as it evolves on its trajectory within this phase space. Now, we're going to do the same kind of analysis in the remaining of the two scenarios. And it can be a bit boring, but please bear with me. All right. So here, what we are in the second scenario, and what we see is that the red line now becomes a Z sigma surface, and that forms a surface of repeller points. We have the fixed point S plus, but we don't have the fixed point T plus. And we have B plus, but unfortunately it lies in the orange shaded region, which means it is neither real. And when we look at this, the trajectories in this phase portrait, we find that we do recover the conformal behavior as we've seen before. And all the trajectories that are starting on the Z sigma plane end up on the equilibrium line, which connects both the S plus and the attractor. Moving forward, again, here I am fixing the initial condition but varying our parameters alpha and beta. So what we see is that when our initial conditions are set, when our initial condition set close to Z sigma surface, the trajectory will end up on the equilibrium line. The value of beta mostly determine where the trajectory ends up on the equilibrium line. If the beta is large, what we find is the trajectory ends near the saddle point S plus, and if it is small, it ends up on A naught. Basically, we do not find any effect on the trajectories when we map alpha to minus alpha or beta to minus beta. Now let's go to the third scenario. So the third scenario is, again, we're going to do the same analysis. What we find is now T plus is here. We don't have B plus fixed point, and what we have is a new radiation dominated point, which is D plus. So here, as we're changing different initial condition, we find that they all end up on the equilibrium line. And if they are on the plane, the Z sigma plane, they also end up on the line. And A naught seems to be an attractor on every single scenario. What else? I think we do recover the conformal behavior when sigma is equal to 0. So when we choose our initial condition from T plus, we find that it ends up at S plus. When we choose our initial condition from D plus, it goes toward A naught. Uh, Now, moving forward, if we fix our initial condition to near S plus and vary our parameters, this is what we find. That mostly, if beta is negative, it tends to get attracted to S plus. Otherwise, it has a tendency to go to A naught. Now that this is done, what we do is we choose one of these scenarios to further analyze. What I mean is we take scenario one and we do a cosmological analysis. So basically all this information helps us to choose what kind of model we want to mimic lambda CDM. Sorry. So in our cosmological analysis, as I said, in scenario one, the model is one where quintessence is coupled to dark matter, and we chose alpha is equal to 0.05 and beta is 1.5. So here, what we do is we take the expansion history and we study it throughout the entire cosmological, in terms of the cosmological redshift throughout from the early universe to present. And we also investigate the mass scale associated with the disformal coefficient, which I mentioned before. So here is a plot of the energy density for the quintessence, radiation, dark matter, and baryon, which was obtained by solving the dynamical system as it evolved from a redshift of 10 to power 4 to present using the 3 different mass scales. So a few of the remarks that we find is that the features of lambda CDM, apologies, this is a typo, lambda CDM, are reproduced as expected, such as the radiation matter transition and the dark matter dark energy transition. What we see is the effect of the different mass scale clearly affect the evolution of the energy density for the quintessence. Sorry, here, these ones for different mass scales, 350, 50, and 15. And we also see that deviation from the conformal framework is more apparent at early universe, so around um, the energy density of the quintessence traces that of a cosmological constant at when a low mass scale is utilized. So basically, as we drop the mass scale use, it tends to be like a constant almost. Sorry. And a larger mass causes deviation from the conformal framework. Now, because in the early universe, we see that the disformal couplings are important, we try to investigate the disformal nature of the dynamical system by defining an effective conformal coupling. This was done in this reference paper, which is defined as this. And we plot alpha effective from throughout the expansion history of the model for the 3 mass scales. And what we observe, or what the remarks that we make, is that when alpha effective is close to 0, the disformal coupling is canceling. And this was shown in a paper in this reference. So basically, I'm talking here when it's close to 0. There exists a turnover point which indicates the redshift at which the contribution of the disformal coupling is the same as the magnitude of the conformal coupling. So basically, at this point of the turnover, both, it's like a battle between the conformal and the disformal, and at this turnover point, they are actually equal. And after the turnover point, we find the decay of the disformal coupling continues until it becomes insignificant. So basically here, the disformal coupling in the past is significant, it decays, becomes almost equal to the conformal coupling, and then it decays further until it becomes insignificant. That the conformal coupling is what is dominating. So that's what I mean. So the effective uh, coupling becomes the initial value that we chose, 0.05, right? And the alpha effective seems to be also sensitive to the mass scale. Um, and we see this because, it affects the redshift at which the turnover point happens. And a heavier mass scale would cause the turnover to occur at a much higher redshift. With this, I think I will end, but I will make some comment of future work. So basically, in this paper, we have exhausted the possibilities of a model that has disformal coupling and mimicking lambda CDM. In future work, what we do is we do a redshift space distortion analysis of the same kind of of model, and we look up into the perturbation theory, and this is something that I'm currently working on. With this, I'm done with what's on the summary board. I'd like to finish and thank you very much. If you have any question, I'd like to take them.
Okay, thank you, Avishek. And as you have said, if anyone has a question, feel free to ask. Okay, we will wait for if there is anyone writing something in the chat. Okay, so there are no questions, but and as we are in a little bit in a delay, we are going to pass to the following speaker. Thank you, Avishek, for your contribution.
Thank you so much. It was a pleasure.